A California farm town just got hit by roughly 18 earthquakes in a single hour, and not one of them was the main shock, because there wasn't one. That missing main shock is really the entire story here. It's the fingerprint of something seismologists call a swarm. And this particular swarm broke out at maybe the single worst address in the entire state, right at the southern doorstep of the San Andreas Fault, a stretch of ground that hasn't ruptured in a major earthquake in more than 300 years. Most swarms in this exact spot fizzle out and go nowhere. This same patch of ground did precisely that back in May, too. But I want to walk you through exactly what scientists are watching right now to figure out which way this particular sequence is going to break. This corner of California doesn't get nearly the same attention as the more famous stretches of the San Andreas further north, the parts running through the Bay Area or brushing past Los Angeles. But among seismologists who specialize in this fault system, the southern tip sitting near the Salton Sea is treated with a very particular kind of respect, precisely because it combines two things you don't often see together: a genuinely restless, noisy neighbor immediately next door, and a long, uncomfortable silence sitting on the fault that actually matters most. A sequence with no main character. It started just after midnight this week, beneath Brawley, California, a small farming town most of the country has never heard of. At 12:14 in the morning, the ground about 7 kilometers south of the city cracked with a magnitude 3. One earthquake at a depth of roughly 10 to 12 kilometers. On its own, that would never make the news. Small earthquakes happen across Southern California constantly. But 17 minutes later at 12:31 a.m., a magnitude 3. 6, the strongest event of the entire sequence, struck almost the exact same spot, just slightly deeper. Then, around 1:58 in the morning, a magnitude 3. 4 followed in the same general location. Here's what makes that pattern genuinely different from an ordinary earthquake sequence. There was no single big jolt, followed by a tail of gradually shrinking aftershocks. There was no main shock at all. Instead, there was a cluster of events, all roughly similar in size, arriving in an irregular, stuttering rhythm with no one earthquake clearly in charge of the sequence. That specific behavior has a name among seismologists. They call it a swarm. And swarms genuinely don't follow the normal rules most people assume apply to earthquakes. Around 36 people scattered across Brawley, Holtville, and Heber, along with some residents just across the border in Mexico, felt that magnitude 3. 6 and filed reports with the United States Geological Survey. There were no injuries and no reported damage. On its own, a night like this is a minor nuisance, not a disaster. The reason this modest cluster of earthquakes is worth several minutes of your attention has almost nothing to do with the earthquakes themselves. It has everything to do with where exactly they happened. This particular patch of ground sits right at the doorstep of arguably the most dangerous quiet fault in the entire country, the stretch of the San Andreas that hasn't produced a major rupture in over 3 centuries. And every single time this doorstep starts trembling, the scientists who study these faults for a living stop what they're doing and look north. So let's actually walk through what happened, what it plausibly means, and the specific, concrete things researchers are watching right now to figure out whether this fades into nothing or becomes the start of something considerably larger. What makes a swarm different? The place all of this is happening is called the Brawley Seismic Zone, and it's genuinely one of the busiest patches of crust anywhere in California. To understand why this matters, you first need to understand why a swarm is fundamentally different from a normal earthquake sequence. When most people picture an earthquake, they picture one big jolt, followed by a string of progressively weaker aftershocks, fading away over hours and days. That's the standard script that comes from a single fault surface breaking, and then gradually settling back down. A swarm simply doesn't work that way. In a swarm, you get dozens or even hundreds of earthquakes clustered tightly together in both space and time, with none of them clearly dominating the rest, switching on and off in bursts that can stretch across days or even weeks. That magnitude 3, 6, that led this week's sequence was never actually a main shock. It was simply the largest event so far, nothing more. What actually drives a swarm tends to be different too. A normal main shock is fundamentally a stress problem. Crust builds up strain gradually until a fault finally snaps under the pressure. A swarm is usually more of a fluid problem instead. Water migrating slowly through cracks in the rock, changing the pressure, acting on a whole network of small faults, and letting them slip a little bit at a time, one after another. That's exactly why swarms tend to ignore the usual statistical patterns. They don't decay neatly the way ordinary aftershocks typically do. They can stall out completely and then restart without any real warning, because the underlying driver isn't a single broken fault gradually relaxing. It's fluid moving through a fractured system, and fluid can start and stop in ways a single fault rupture simply cannot. That distinction matters for one genuinely practical reason. In a normal sequence, once the big one has already happened, the worst is statistically behind you. In a swarm, you never really get that same reassurance because there's no clean main shock to point back to in the rearview mirror. The largest event of this particular sequence might have already happened this week, or it might still be building. That uncertainty is baked directly into the underlying physics of the situation. And it's exactly why a modest cluster of magnitude 3 earthquakes gets treated with far more seriousness in this specific location than it would almost anywhere else in the country. This has happened before, recently. If this week felt oddly familiar to people living around Brawley, that's because it genuinely should have. This isn't the first time this exact patch of ground has behaved this way, and it isn't even the first time this year. Back in May, this same underlying structure produced a considerably larger swarm. It began with a barely noticeable magnitude, 1, 6, several miles beneath the city, climbed through a magnitude 3, 5, that same afternoon, and peaked just after midnight with a magnitude 4. 7, strong enough to wake people out of bed and generate felt reports as far away as San Diego, well over 200 kilometers from the epicenter. By the time that swarm finally wound down, monitoring agencies had cataloged several hundred separate earthquakes, and the city of Brawley had activated its emergency operations center, before eventually shifting to lighter, virtual monitoring once the activity settled down. That May swarm is genuinely the key to reading this latest one, because it tells us exactly what this underlying structure is capable of producing when conditions line up just right. The same buried fault system also lit up back in the winter of 2016 and early 2017, meaning we're now looking at the same underlying structure reactivating across multiple separate episodes spanning roughly a decade. The winter of 2016, this past May, and now again this week, swarms restarting on the same fault system across months and years is genuinely documented, well-understood behavior for this particular zone. It's simply what this stretch of crust tends to do over and over. But every single restart resets the clock on the one question nobody can reliably answer in advance. Where exactly does this particular sequence eventually top out? A rough historical ceiling. The wider neighborhood around Brawley has a considerably longer track record, and it tells you roughly where the practical ceiling actually tends to sit. Back in 2012, a swarm just north of this week's location produced 2 separate earthquakes above magnitude 5, a 5, 3, and a 5. 5, along with hundreds of smaller shocks, and it caused minor damage around Brawley at the time. In 1981, the Westmoreland earthquake reached magnitude 5. 8, though that particular event behaved more like a conventional main shock followed by aftershocks, rather than a pure swarm. And in 2020, another swarm centered near Westmoreland grew active enough that the Geological Survey issued a formal aftershock forecast, before activity eventually settled back down, with more than 60 earthquakes above magnitude 3 recorded during that particular episode. Put all of that together, and you get a rough working ceiling for swarm-type sequences in this specific zone, somewhere in the neighborhood of magnitude 5.5. Big enough to break windows and crack plaster, but historically not the kind of event that levels an entire region on its own. The real reason this zone matters. To understand why anyone living north of Brawley should genuinely care about any of this, you have to look at what this particular seismic zone actually connects to. The Brawley seismic zone isn't just some random patch of active ground. It functions almost like a geological junction box, the specific place where the northern end of the Imperial Fault hands off plate motion to the southern end of the San Andreas Fault near the bottom of the Salton Sea. When the Brawley zone shakes, it's shaking right at the base of the San Andreas itself. And the specific stretch of the San Andreas that begins right there happens to be the exact segment that genuinely keeps seismologists up at night. The southernmost San Andreas, running along the northeastern shore of the Salton Sea, past a small community called Bombay Beach, and up toward the Coachella Valley and greater Los Angeles beyond it. That particular section has a real problem. The problem is silence. It hasn't produced a major earthquake in at least 300 years. Detailed trenching studies published back in 2011, based on digging directly across the fault and carefully dating the disturbed soil layers, worked out a chronology showing this section tends to rupture on average roughly every 180 years. Run that math, and this particular section of fault isn't simply due for another rupture. It's genuinely well past due, based on that historical average. So when a swarm fires off right near the connection point feeding into that fault, the question basically writes itself. Could the small earthquakes rattling this doorstep somehow give the much larger sleeping fault next door the nudge it eventually needs to finally let go? That's genuinely the real story underneath all of this, and it remains a legitimately open scientific question, rather than something settled confidently in either direction. Weighing the real risk. The honest answer to whether a swarm like this can trigger a major San Andreas rupture is that the underlying mechanism is real, but it's weak, and distance turns out to matter enormously. Earthquakes do change the stress acting on nearby faults, but a magnitude 3 or 4 event only does this meaningfully across a range of a few kilometers at most. So the genuine concern would be far greater if a swarm like this were happening directly on top of the San Andreas terminus itself. This week's swarm sits roughly 60 kilometers south of that terminus, close enough to keep the underlying question alive, but far enough away that the actual stress it's adding to the San Andreas itself remains genuinely small, considerably smaller than if this same activity were happening right at Bombay Beach instead. In documented cases from around the world, only a small handful of earthquake swarms have gone on to precede much larger earthquakes nearby. The overwhelming majority simply don't. They rise, sputter for a while, and then fade back into background activity. It would honestly be irresponsible to sell you fear here without also giving you the realistic base rate. The single most probable outcome for this sequence is that it behaves essentially the same way the May swarm did, climbing for a while, maybe producing something in the magnitude 4 range, rattling some windows, and then gradually dying out over the coming days to weeks without producing anything larger. That's genuinely the base case, and it's where the smart money sits if you had to place a bet on it. Across earthquakes worldwide, only somewhere between roughly 5 and 10% of moderate shocks turn out, in hindsight, to have been foreshocks preceding something considerably larger. The catch, and it's an important one, is that there's no reliable way to identify a foreshock in advance. It only earns that specific label retroactively after the larger earthquake actually shows up. Until then, it remains statistically indistinguishable from the thousands of other earthquakes that lead to absolutely nothing at all. So if anyone tells you with total confidence that this week's swarm was definitely the foreshock of some coming major earthquake, they're claiming a level of predictive power that no seismologist on the planet actually possesses. What the real, proven hazard looks like. It also helps to keep in mind what the genuinely proven, documented hazard around this region actually looks like, because it isn't the swarm itself. The faults connected to the Brawley Zone carry a real, well-documented history of destructive earthquakes. The Imperial Valley produced twin magnitude 6, 2 earthquakes about an hour apart back in 1915. The El Centro earthquake of 1940 reached roughly magnitude 6. 9 on the Imperial Fault, 1979 brought a magnitude 6. 5 to that same valley, injuring dozens of people. 1987 delivered a magnitude 6. 5 near Superstition Hills. And in 2010, the El Mayor Cocapa earthquake, striking just across the border in Mexico, reached magnitude 7, 2. Those are genuinely the events capable of damaging buildings and hurting people in this region. The swarm activity is really more of a noisy symptom by comparison. Those larger, well-documented faults are the actual reason residents throughout this valley keep an earthquake kit ready in the closet. Still, there's a legitimate reason to keep watching this particular zone closely, and it isn't simply hype for its own sake. This is genuinely the one place in California where the Geological Survey has an actual operational protocol, allowing it to publicly raise the estimated odds of a San Andreas rupture in something close to real time. It has a documented historical ceiling, a documented habit of restarting across years and decades, and it has already prompted the agency to formally act on at least a couple of prior occasions. An ancient lake and a loaded spring, there's a genuine unresolved mystery sitting underneath this entire story, and it's worth pausing on because it's really the thing that should hold your attention most. The noisiest patch of crust in Southern California sits directly at the foot of arguably the quietest major fault in the entire state. The Brawley Zone swarms, pauses, and restarts almost continuously across the years, while the southern San Andreas, sitting just a few dozen kilometers away, has done essentially nothing for 3 full centuries. And it's that quiet fault, not the noisy zone, that carries the real potential to hurt people. Researchers have a leading theory for why the particular section has stayed silent for so unusually long, and it involves a lake that no longer really exists in its historical form. For thousands of years, the Salton Trough was periodically filled by an enormous ancient body of water known as Lake Cahuilla, far larger than today's shrinking Salton Sea. Research published in 2023 found something genuinely striking. The last several major ruptures along the southernmost San Andreas each appear to line up closely with periods when that ancient lake was full. The sheer weight of all that water may have been acting almost like a natural trigger, helping the fault release its built-up strain on a somewhat more regular schedule throughout history. That lake has been largely gone for centuries now, and that absence may be exactly why the fault's internal clock appears to have slowed down so dramatically. Here's the genuinely unsettling part of that theory. If the ancient lake was actually helping this fault release its accumulated strain on schedule, then losing the lake never actually made the fault any safer. It simply removed one of its natural triggers. The underlying strain has kept quietly accumulating this entire time regardless, with several meters of it now believed to sit within that section of fault. The ongoing silence isn't the same thing as safety. It looks a lot more like a loaded spring with its safety catch stuck in place. What happened the last time this mattered? The clearest historical precedent for how seriously scientists take a swarm in this particular area comes from 2016, when activity broke out right at Bombay Beach, essentially right at the fault terminus itself. That September, a swarm of roughly 100 earthquakes, topping out around magnitude 4. 3 broke out directly at the southern tip of the San Andreas. And because it happened right on top of the fault itself, the Geological Survey did something it almost never does. It ran the underlying probability numbers in real time and publicly raised the estimated odds of a magnitude 7 or larger earthquake, striking the southern San Andreas within the following week to as high as 1 in 100. For context, the normal background odds in any given week typically sit somewhere around 1 in 6,000, meaning that represented roughly a 100-fold jump. California's Office of Emergency Services issued a formal earthquake advisory for a few days, and the state was genuinely, openly bracing for the possibility. Then, nothing happened. The swarm gradually faded. The elevated odds decayed back toward background levels within about a week, and the advisory quietly lapsed without incident. That outcome wasn't a failure of the underlying science. It was the science working exactly as intended. A 1 in 100 chance still means nothing happens 99 times out of 100. 2 things from that episode are worth holding on to. First, this entire system is genuinely built around public disclosure rather than concealment. And second, the reason the odds spiked so dramatically in 2016 and would likely be considerably lower for this week's activity comes down to that one governing variable: distance to the fault terminus. Bombay Beach sat right on top of it. This week's swarm sits roughly 60 kilometers away. A coincidence. Worth debunking. There's one more piece of this story worth addressing directly, because plenty of people are likely encountering it online already, framed in a deeply misleading way. On the very same night as this week's Brawley swarm, roughly 3 hours later, a genuinely rare magnitude 5. 0 earthquake struck the Texas Panhandle near a small town called Spearman, reportedly the strongest earthquake to hit that specific region in over a century. Within hours, posts began circulating online claiming the 2 events were somehow connected, implying some kind of continental scale link. Let's take that claim apart cleanly, since dismantling it honestly is more useful than simply ignoring it. These 2 earthquakes were roughly 3 hours apart, not simultaneous, and they occurred more than 1,600 kilometers apart from each other. The stress that one earthquake can meaningfully transfer to another fault fades away within just a few kilometers, for a magnitude 3 or 4 event, and within a few dozen kilometers even for something closer to magnitude 5. There is no known physical mechanism connecting a swarm in California to a moderate earthquake in Texas, 1,700 kilometers away. What you're actually looking at is simple coincidence, plain arithmetic. This planet produces roughly 150 earthquakes of magnitude 4, 5 or greater every single week worldwide. 2 unusual events landing on the same general night isn't evidence of some hidden pattern. It's simply what ordinary randomness looks like at a global scale. That Texas earthquake is genuinely its own separate and interesting story on its own merits, but it has nothing whatsoever to do with what happened near Brawley. 3 signals worth tracking yourself. So here's the part promised at the start of this video. The specific, concrete things scientists are actually watching right now to determine whether this week was just background noise or the early opening of something more serious. There are essentially 3 signals, and you can track them yourself. The first is magnitude. If the swarm eventually climbs past May's peak of 4, 7, and especially if it pushes anywhere close to this zone's historical swarm ceiling of roughly magnitude 5.5, that meaningfully changes the underlying risk picture, since a magnitude 5 releases roughly 700 times more energy than this week's magnitude 3. 6. Events climbing, rather than gradually fading, is the first genuine red flag worth watching for. The second signal is direction. Pay attention to where the earthquakes are actually moving. If activity stays contained beneath Brawley itself, that remains the reassuring scenario. If it instead starts migrating north, toward Westmoreland, toward the geothermal field, and especially toward Bombay Beach and the San Andreas terminus itself, that's the scenario that genuinely matters most, since that's exactly the direction that would carry a swarm from 60 kilometers away into the kind of situation seen back in 2016. Location genuinely is everything with this particular hazard, and migration northward is the single most important thing to track. The third signal is official confirmation. If the Geological Survey issues a formal aftershock forecast, or the state issues a genuine earthquake advisory, the way both happened in 2016 and again during the 2020 Westmoreland swarm, that's your clear cue that professionals have already run the real-time numbers and decided the underlying odds have shifted enough to say so publicly. Where this actually leaves us. Let's bring this back to where it started this week. The ground beneath Brawley began shaking again in that same stuttering, no main shock rhythm it produced back in May, and in 2016 before that. The most likely outcome, by a wide margin, is that it does exactly what it has done every one of those previous times. It rises, rattles a little, and gradually fades out over the coming days without producing anything larger than a moderate earthquake. If you happen to live in that area, the realistic thing to actually prepare for is a few more restless nights, not some looming catastrophe. But the reason any of this remains genuinely worth watching isn't really the swarm itself, it's the much larger fault sitting right next door, the southernmost San Andreas, silent for more than 3 centuries, carrying several meters of quietly stored strain, sitting roughly 60 kilometers from a patch of ground that simply won't stop trembling. Science can reasonably estimate the odds that any given swarm nudges that larger fault awake. And right now, those odds remain low. What science genuinely cannot yet explain is why the most heavily loaded section of arguably the most famous fault on the planet has managed to stay so remarkably still while everything immediately around it keeps shaking. Or which swarm, if any, eventually ends that long silence for good. Living with an uncertain neighbor. For the people who actually call this stretch of the Imperial Valley home, none of this uncertainty is purely academic. Brawley, Holtville, Heber, and the smaller communities scattered around the Salton Sea have all built a kind of quiet, practiced familiarity with this rhythm of restless nights, followed by calm stretches. Emergency managers in the region already have protocols in place specifically built around swarm activity, distinct from the standard earthquake response plans used elsewhere in the state, precisely because this zone behaves so differently from anywhere else in California. That familiarity cuts both ways, though. It can breed genuine expertise and preparedness, but it can also breed a kind of fatigue, where each new swarm gets waved off a little too quickly, simply because the last 5 did. Scientists studying this region are careful to walk that line themselves, treating every new sequence as worth watching closely without letting the historical pattern of false alarms lull anyone into complete complacency. Given what's sitting quietly next door along the southern San Andreas, that balance between calm and vigilance is exactly the one this entire region has to keep striking, swarm after swarm, for as long as that ancient fault continues waiting its turn.